Am I audible?
Yes, sir.
Yes, sir.
Okay. तो 5 मिनट वेट कर लेते हैं, बाकी स्टूडेंट्स को ज्वाइन करने दो, है ना, जब तक मैं तुम लोग को शेयर कर देता हूँ, लेक्चर्स बहुत सारे शेयर नहीं किए हैं।
Okay, sir.
चलो स्टार्ट करते हैं। बाकी लोग कहाँ है क्लास के? आप लोग बहुत कम अटेंडेंस रहती है आजकल। बाकी कहाँ है?
सर उन्हें लगा होगा कि आज क्लास नहीं होगी, ये पता
तो
नहीं नहीं है।
आज की क्लास नहीं होगी? मैंने आपको बोला था ना मंडे से क्लास होगी।
हाँ सर, पता था कि क्लास होगी।
बाकी क्लास सही चल रही है?
हाँ सर, अच्छी चल रही है।
चलो ठीक है। तो in last class we have solved the pipe flow problem, pipe flow of inside the pipe due to the pressure difference, and the falling film problem for the uh, power law fluids. Okay, this in this class we will solve the same problems, tube flow problem and the falling film problem for the Bingham fluid. Okay, so first we write the Bingham equation. So first problem is tube flow problem for the Bingham fluid. So basically you have a pipeline and fluid is flowing inside the pipeline due to the pressure difference. The same problem which you had solved for the power law fluids as well as for the Newtonian fluid. In the last class we had solved this problem for the power law fluids, and in the transport phenomena class we have solved this problem for the Newtonian fluid. So this is the R axis, this is the Z axis. Fluid is flowing due to the pressure difference. Here the pressure is P naught, here pressure is PL. The length of the pipeline is L. Okay. So we will start solving the problem by the diameter is R, capital R. So this is for the this solution is for the Bingham fluid. Okay. So we will start with the assumptions. The all the initial steps are same. First you have to write the assumptions. Only difference is here you have assumed that viscosity is not constant. And now in the Newtonian fluid we assume that viscosity is constant. Here we cannot assume viscosity is constant because it is a non-Newtonian fluid. Second assumption is that we cannot assume it is a Newtonian fluid. And this is the second point. And in the Newtonian fluid solution, we assume the viscosity is constant, viscosity and density is constant. In this case, only density is constant, viscosity is not constant, and this is not a Newtonian fluid, this is a Bingham fluid. Okay, so these two points will change. Otherwise, steady state conditions, density is constant, no slip boundary conditions, and end effects are negligible. These all conditions will be applicable. Okay, then you have to write the viscosity profile like the previous case. So you have the viscosity Vz, which will depend upon R only, other components will be zero, and you have the shear stress component tau Rz, which is not zero. Other eight components are zero. Okay, so these are the two quantities. Then you have to take the after this you have to take the equation of motion. Okay, so this is the cylindrical system. So for cylindrical system you have to take the cylindrical equation of motion. So first open the equation of motion table. So these are the equation of motions. This is equation of continuity, this is the equation of motion. So in equation of motion we will take the cylindrical coordinate system. So this is the cylindrical coordinate system. Okay, just copy this equation of motion from the table. You need not to memorize this table, you have to just copy this. Okay, copy image, just copy this image and paste in the here. Okay, so these are the equation of motion in cylindrical coordinate system. Okay, these three are the equation of motion in the cylindrical coordinate system. You need not to remember this, and you have to remember the original equation of the equation of motion in the vector and tensor form, but you need not to remember in the detailed form because it is given for to you, and it is very difficult to remember. It is not required to remember. Okay, equation of motion in the cylindrical system. Okay, now in this equation you have to drop out the zero the components which are zero. Okay, Vr is zero, so these all components will be zero. V theta is zero, Vz is not zero, but Vr is zero, V theta is zero, this will be zero. Again, this will be the initial stages are same. And in the previous case also we have done the same thing. So these all components are zero. In this step also, all these components are zero. This is zero. Tau r theta is zero. Tau theta is zero because you have only the two non-zero quantity. Velocity is non-zero. Vz is not zero. Tau rz is not zero, and pressure drop P is not zero. Okay. So here all components, all other components are zero. You have to search for tau rz. This is the tau rz. This is not zero. Vz is not zero, but Vz will not depend upon Z. Okay, this comes from the equation of continuity. So from equation of continuity, you can say Vz will not depend upon Z. So this term will also be zero. All other terms are zero. Vz does not depend upon time because steady state Vr is zero, V theta is zero. So these all at the right hand side, this equation, all the terms are zero. This term will be not zero. This term will be not zero. V theta z is zero, V z z is zero, G z is zero. Okay, so you will get these two equations. Okay, now you can solve. In the last class we had already solved this equation for the power law fluid. Okay, so when you solve this equation for power law fluid, you will get final equation. This is 1 by rho del P by del Z minus 1 by rho 1 by rho r, r is the radius, del by del r tau rz equal to 0. This is the equation. Now in this equation, because this term depends upon Z, this term depends upon R. This depends upon R, this depends upon Z. So you can separately solve this. In the differential equation, if two terms are totally different, then you can separately solve that two terms that will not depend upon each other. Basically, both. So when you solve the first term, you will get P naught minus PL divided by L from this term. Rho you can take rho common, rho cannot be zero, so the other terms will be zero. Okay. Now plus del by del r, 1 by r, del by del r in bracket r tau rz equal to 0. So you can take this here at the other side and solve this equation. Finally you will get tau rz equal to P naught minus PL divided by 2L R plus C1 divided by R. From the first boundary condition, you can say fluid is symmetric, flow is symmetric across the system. So at the middle point, the shear stress value is 0. So C1 is the integral constant. You had already done this in the previous classes. So C1 should be 0. I had already explained you why the C1 is 0, because system is symmetric. So you will get tau Rz equal to T naught minus TL by 2L multiplied by R. So this is equation number 1. Till this point, solution is same for the Newtonian fluid for all types of non-Newtonian fluids. Okay. So we had already solved this problem for the power law fluid in the previous class. Today we will solve for the Bingham fluids. Now the solution will be different from this point. So now we have to substitute the value of tau Rz according to the Bingham fluid model. Okay. So now we can write in the next page for Bingham fluids. Bingham fluids means fluids which behaves like the paste. Okay, so at the lower shear stress, they behave like the solid material. At higher shear stress, they behave like a fluid, Newtonian fluid. Okay, so we will put the Bingham fluid model. So what the Bingham fluid tells that if tau Rz is less than tau naught, which is a constant. Okay, so this point comes at R equal to R is less than R naught. This is the point between the system. When R is less than R naught, then dVz by dr equal to 0 or Vz equal to V naught. Okay, if this is a 0, that means Vz is constant, that is equal to V naught, which is a constant. Okay, so this is the first point. And second point, if tau Rz is greater than tau naught, greater than and equal to tau naught, or R is greater than and equal to R naught. R naught is a diameter in radius inside this system. Okay, so suppose this is the R naught. This distance is R naught. Okay, so it is the distance from where up to that point fluid behaves like a fluid. The material behaves like a fluid. Okay, so I will make more clear diagram so you can understand. Suppose this is a pipeline. So if fluids flow like paste, you all have seen the paste. So when the paste comes out, it's like a solid tube. So how it's behaved? So I am making the velocity profile. So how the fluid, this Bingham fluids behaves. Okay, so this is the typical velocity profile of the Bingham fluid. So at near to the wall, so near to the wall, so this is the velocity profile. How the velocity profile looks in for the Bingham fluid. So basically this diameter is R naught. Okay. So up to this diameter, up to R naught, you will see that the velocity is high. That means shear stress is low. So when the shear stress is low, then it will behave like a solid material. Here it is a flow is same, and the velocity is same at every point. So it will behave like a solid material. From R naught to capital R, from R naught to capital R, this is capital R. So from R naught to capital R, it behaves like fluid. So only from this scale, from this distance, it behaves like fluid. Okay, so that is the same you have seen in the toothpaste. So in the toothpaste, the most of the material comes out as a solid tube, and only the at the wall it looks like a fluid, and at the wall of the tube it looks like a fluid is coming out. Otherwise, at the middle of the part it looks like a solid material. Okay, so this is the velocity profile of the Bingham fluid. Now we have to solve the problem for this velocity profile. Okay, so there are two cases. In first case, when tau is less than tau naught, that means for the middle of the part, this part for the middle part, the velocity is constant, which is equal to v naught, and for the when the tau rz is greater than tau naught, means at near to the wall, you have the eta equal to mu naught plus tau naught divided by in bracket dvz by dr. Okay, and then tau rz equal to minus eta in bracket minus eta multiplied by dvz by dr. This is the equation. Okay, now first you have to, this is the constant. Here you need not to solve again for the first point. For first point you have already have the solution. For second point, this is equation number 2. For the equation number 2 you have to further solve the problem. Okay, so from equation number 2, first you have to remove the mode sign. So what I have told you that if value of shear rate is positive, if shear rate is positive, then after removal you have the positive sign. If the shear rate is negative, then after removal you have the negative sign. So in this case, you can see that when you go to the positive direction of R, when you move in the positive direction of R from here to here, the value of shear stress is reducing. Okay, so then that means you have the dvz by dr is negative. Okay, so you can see basically the when you move in this direction, value of the velocity is reducing. So when you move in the positive direction of r, value of velocity is reducing. That's why dvz by dr is negative, because when you add the r, then vz is reducing. So this quantity should be negative. Enough. So you can write here when r is positive or the variation is in r is positive, variation in r is positive, comma, the variation in velocity is negative. Okay, so you can say that's why dvz by dr is negative. So eta equal to mu naught minus tau naught divided by dvz by dr Now substitute this equation number 3, substitute the equation in the equation. Suppose this is equation number 3, this is equation number 4, this is equation number 3, this is equation number 4. Now substitute equation number 4 in 3. You will get tau Rz equal to, in bracket, minus mu naught minus tau naught divided by dvz by dr, bracket close, multiply by dvz by dr. Now just solve this, open this bracket, you will get tau Rz equal to minus mu dvz by dr plus tau naught. This is equation number 5. Okay. Now you have to, for solving this equation, first you have to know the value of tau naught. Okay. So how you calculate the tau naught? So that is calculated by the condition of movement of fluid. So when you start to pressurize the fluid, suppose there is a tube where the fluid is a Bingham fluid is flowing. So initially when you push the fluid will not flow. Okay. So when you move with the fluid from a critical pressure, above a critical pressure, then the velocity profile starts to develop. Okay. So basically what I am trying to say that, suppose this is a pipeline which is filled with a Bingham fluid. Okay, so Bingham fluid is like a gel. Okay, so suppose here pressure is P naught, here pressure is P naught. If P naught is and P naught are equal, then there is a no flow. And because it is a gel type material, fluid cannot flow automatically. You need the pressure. Suppose you put the pressure P dash. Okay, now P dash is very small. The difference delta P, that is equal to P naught dash minus P naught, that is very small. Okay, so suppose this is the value of this, the magnitude of this pressure is less than tau. Okay, less than tau naught. So what will happen? Fluid will still not flow. Okay, when P naught minus P dash naught minus P dash equal to tau naught, then fluid start to flow. Okay, then at the boundary only, they will start to flow. Okay, when P naught dash minus P naught is greater than tau naught, then they will start, then what will happen? You have a proper velocity profile, है ना? So initially, suppose you are differentially increasing the flow rate, increasing the pressure drop, है ना? Slowly you are increasing the pressure drop. So initially you have the very less amount of fluid which is flowing as a Newtonian fluid. Most of the fluid is flowing in the Bingham fluid. Now you again start increase the pressure drop, then this layer will be, the thickness of the layer which is flowing as a fluid, that will increase, because at most of the point the value of shear stress is now higher. Now again you increase the shear stress, now this value will again increase. Okay, and after some time, if the value of the shear stress is much higher, value of the pressure drop is much higher, then you have the total Newtonian flow. Okay, so here the value is changing, value of pressure, if the pressure drop is changing, pressure drop is increasing, then you have the transformation from the Bingham fluid to the Newtonian fluid. Okay, based on the value of the shear stress. Okay, so this is the condition to for the movement of the fluid. Okay, so we can write here condition for movement of the fluid. So as we start to pressurize fluid by imposing pressure, difference the fluid does not move initially. Fluid does not move initially. Okay. As we continue to increase the pressure difference initially. So this is the condition when you have the tau rz at the wall, when you have the tau rz at r equal to capital R at the wall should be less than tau naught. है for this condition. Okay, this is the first point. Now at the second point, as we continue to increase the pressure difference, the fluid starts to move. So when the fluid starts to move, when tau rz at r equal to capital R at the wall is equal to tau naught, then only fluid starts to move. है Now if we again continue to increase the pressure difference, what will happen? Some of the fluid will flow like a Newtonian fluid and some of the part fluid flow like a Bingham solid material. For some of the reason, fluid behaves like Newtonian fluid, and in some of the reason fluid behaves like solid material. And combine of both is the Bingham fluid, like solid material. Okay, and combination of both is the example of Bingham fluid. So at this point where fluid behaves like a solid material, where the velocity is not changing, this is basically the region where fluid behaves like a solid material. Where the velocity is changing, there it behaves like a Newtonian fluid. Okay, so basically the Bingham fluid, it looks like some of solid material, some solid material is floating inside a fluid. Okay, so it looks like that. Okay, and in this case you can say tau rz at r equal to r naught should equal to tau naught, where r naught should be less than capital R. Okay, so the radius r naught should be less than capital R. Okay, here r naught is equal to r, capital R, and in this case r naught is greater than capital R, so you will have the only solid part. The fluid cannot move. Okay, now we will solve the problem. So again comes to the original equation, equation number 1, that is tau rz equal to p naught minus pl by 2r. That equation we have developed by the equation of motion. So from equation of motion we know that from equation 1 we know that tau rz equal to p naught minus pl divided by 2l multiplied by r. Okay, so this is equation number 1. Now for the condition now we will solve, first we will solve when the fluid just started to flow. Okay, so you have just put the significant amount or sufficient amount of pressure that just fluid starts to flow. Okay, at that case, when, or we can write case by case. So first I am writing the case number 1. When fluid just started to flow. So I had already told you, if the fluid just started to flow, so tau rz at r equal to capital R should be equal to tau naught. Just substitute the value at r equal to capital R, tau equal to tau naught from equation number 1. You know that tau naught equal to pressure. Here we are writing the P naught L and P naught. We can write, because here the pressure is varying, and also we will give the some new notation for pressure. So P naught dash minus PL dash. This is the new pressure which is sufficient to make the fluid flow. 2L multiplied by capital R. Okay, so this is equation number 1. If fluid start, and when the second case, when fluid flows sufficiently, when you have the sufficient pressure drop. Case number 2, when pressure drop increases significantly, or the pressure drop further increases, then tau naught should be less than or equal to P naught minus PL divided by 2L R. And from equation number 1. This is not equation number 1, this is from equation number 1. Okay. Now suppose, and this pressure P naught dash minus PL dash, that is called the critical pressure. Critical pressure is the pressure where the fluid starts to flow. Okay. So we will also write here pressure P naught dash minus PL dash equal to critical pressure. Is the critical pressure. Okay. So when the value of pressure drop exceeds from this value, then only you have the flow. Otherwise, you don't have any flow. Okay. Now we will solve the problem again. So tau RZ equal to, from equation number 1, tau RZ equal to P naught minus PL divided by 2L multiplied by R. Okay. Now at R equal to R naught, at R equal to R naught, R naught is the distance till there fluid flows like a Bingham fluid in a very solid body. Tau RZ equal to tau naught, tau RZ equal to tau naught. So just substitute the value. So you can say tau naught equal to P naught minus PL divided by 2L R naught. Now from this equation you can calculate the value of R naught. So R naught equal to, then R naught equal to 2L tau naught divided by P naught minus PL. So basically R naught is unknown, tau naught is known, and tau naught is the property of fluid. Okay, so you always knows the value of tau naught. Suppose I am giving you, this is this type of material, this is a type of gel, and I am giving you some name. Okay, this is the silica gel or any gel, है so for that type of material, you should know the value of like the value of viscosity is known for the fluids, and for the value of viscosity for water, value of viscosity for NF10. These are the known quantities, and this is the physical property of material. Similarly, tau naught is also a physical property of material, which should be known, but R naught depends upon the structure and for the geometry of the flowing channel. So the value of R naught you have to calculate it during the derivation. Okay, so here what we have done, we calculated the value of R naught, which is unknown. Okay, so this is equation number 6, I think. This is equation number 6. Okay, now we will start to solve. Once you know the value of R naught, then only you can solve the problem. Okay, so for R is less than or equal to R naught, until unless you don't know the value, you cannot make the boundaries from where you have for which boundary you are solving the problem. So for R is less than or equal to R naught, we can calculate the value of, or for R is less than R naught, equation number 1 is applicable. One minute. For R is greater than R naught, है ना. Equation number 1 is applicable for R is greater than R naught. One and two are applicable. The equation number 1 is this. So this is applicable for hold the boundary. Then you have equation number 2. So this equation number 2 is only applicable when R is greater than or equal to R naught. Okay. So we are solving for the same condition when R is greater than or equal to R naught. Greater than and equal to R naught. Okay. So you can write minus mu dvz by dr plus tau naught. This is the value of tau rz. From the equation number 5. From equation number 5, it is given that tau rz equal to minus mu dvz by dr plus tau naught. Okay, so this is from equation number 5. From equation number 5. That should be equal to, from equation number 1, that should be equal to P naught minus PL divided by 2L multiplied by R. Okay, now just you have to solve this problem. This is a simple derivative equation. You can easily solve this problem. This will become minus mu dvz by dr equal to P naught minus PL by 2LR minus tau naught. Tau naught comes here. Now just again rearrange this dvz by dr, that is equal to P naught minus PL minus P naught minus PL divided by 2 mu L R minus plus tau naught divided by R, tau naught divided by mu. Okay, now integrate this equation, you will get the Vz equal to tau naught divided by mu. This is the positive quantity multiplied by R minus in bracket P naught minus PL divided by 4 mu L multiplied by R square plus C2. C2 is the integral constant again. Okay. Now the second boundary condition. You can say at R equal to capital R, Vz equal to 0, no slip boundary condition. So once you substitute at R equal to capital R, Vz equal to 0, you will get the value of C2. So C2 will come as, just sign will change, P naught minus PL divided by 4 mu L multiplied by R to the power R square, capital R square, minus tau naught divided by mu R. So this is the value of C2. Just substitute the value of C2 in equation number, this is equation number 7. Substitute the value of C2 in equation number 7. You will get Vz equal to tau naught divided by mu in bracket R minus capital R plus P naught minus PL in bracket P naught minus PL divided by 4 mu L multiplied by capital R square, bracket close, second bracket 1 minus R divided by capital R square, bracket close. So this is the velocity profile when R is less than R naught, or R is greater than or equal to R naught. When R is greater than or equal to R naught. Okay, and R naught should be equal to 2L tau naught divided by P naught minus PL. Okay, and R naught equal to, where R naught equal to, so R naught equal to 2 tau naught L divided by P naught minus PL. Okay, so these are the quantities. Okay, now second condition is, at if tau is, second condition, if R is less than R naught, then Vz equal to V naught. We have calculated before. Now you have to calculate the value of V naught. Here you have calculated when R is less than R naught, dVz by dr equal to 0. So Vz equal to V naught, a constant value. Now you have to calculate this value of V naught. What is the value of V naught, which is constant? Okay, now we have to calculate the value of V naught. Okay, so for calculating the value of V naught, first we can say at R equal to R naught, here we are taking a basic consideration. Okay, so what is the consideration? That at R equal to R naught, the velocity should be systematic, and the velocity profiles are generally the regular profile. They cannot be discontinued. And at a given point, there should be only one velocity. And it is not possible that at a position, at a given point, there are two different velocities. And at a given point, there fluid is flowing in one direction. At a given point, you have a one velocity. And either it is a 2 liter per, it is a 2 meter per second, or it is a 3 meter per second, or it is a 4 meter per second. It is not possible that at a given point you have the two different velocities. Okay, so here we assume that at R equal to R naught, there should be only one velocity. That, and from equation number, this is equation number 8, and from equation number 8, you know what is the velocity from equation number 8, which should be equal to, and from equation number 8 you can say at R equal to R naught, velocity should be equal to Vz, that is equal to tau naught divided by mu. So in place of small r, we have to write R naught minus R plus, in bracket, P naught minus PL divided by 4 mu L multiply by capital R square, bracket close. In second bracket, you have 1 minus R naught divided by capital R whole square, bracket close. Okay, so this is the equation. Okay, so now what is our next consideration? That is, if r is when we move in a negative direction, है ना? So for all r less than r naught, for all condition where r is less than r naught, vz should be equal to this is vz at r equal to r naught. Okay, so the next condition is for all r which is less than r naught. Okay, so if you check the diagram, so here we have calculated the value of r naught at this point. Okay, at this point we have calculated the value of vz which at r naught. Okay, now when you move in, if r is less than r naught, then you have a constant velocity that should be equal to vz at r naught. Okay, so for all r less than r naught, vz should be equal to v naught, and that should be equal to vz should be equal to v naught, and that should be equal to vz at r equal to r naught. Okay, so we can say v naught equal to tau naught divided by mu r naught minus r plus p naught minus pl divided by 4 mu l multiply by capital R square multiply by 1 minus small r divided by capital R to the power whole square. Okay, so this is equation number 9. So equation number 8 and 9 represents the velocity profile for the fluid flow inside the tube. Bingham fluid flows inside the tube. Equation 8 and 9 represents the Bingham fluid flow inside the tube. Okay, I think this is enough for today's class. In next class, we will solve the next part, which is the falling film problem for the Bingham fluid. Okay, that is also similar to this problem. We will solve the falling film problem. We are using the Bingham fluid. किसी को पूछना है कुछ इसमें से? Basically, the mathematically problem is more easier when we are solving for the Bingham fluid. It is almost similar to the Newtonian fluid, but conceptually it is very difficult to understand. And Bingham fluids problems are very favorite for the examiners generally. And in the fluid mechanics, in the transport phenomena, these problems are very favorite to for the examiners, because mathematically it is very easy to solve, but for conceptually it is very difficult to understand Bingham fluids. So just go through the derivation, and if you have any problem or any confusion, then ask me. ठीक है? और किसी को कुछ पूछना है?
No, sir.
चलो. So next class will be on Wednesday.
Yes, sir.
चलो ठीक है.